To support our discussions with the world's leading thinkers, please see the video description or visit eism.eu/support. Thank you.
Hello and welcome to A Theory of Everything. Today we're talking to Donald Hoffman, a cognitive scientist at the University of California, Irvine, about his recent book, The Case Against Reality. Hoffman has become immensely popular and controversial because of his compelling argument that humans haven't evolved to perceive truth. Truth, he argues, is more fundamental than anything in space-time. He refers to this more fundamental level of reality as a network of conscious agents. In today's exchange, we explore what Hoffman's ideas imply about the fact that the planet is full of nuclear weapons. Are these weapons just an illusion? Stay tuned for Hoffman's response. As Curt Jaimungal from the TOES podcast astutely points out in his massive technical dive into this, Hoffman's argument against reality is founded on the assumption that in evolutionary theory, all possible fitness payoffs are equally probable. Hoffman acknowledges the centrality of this assumption and issues a challenge for anybody to provide an alternative framework to demonstrate why some fitness payoffs are more probable than others. As I point out to Hoffman, renowned theoretical physicist Yakir Aharonov's two-state vector formalism does exactly this. It suggests, with great mathematical rigor and compelling empirical evidence, that Hoffman's assumption of equal probability in fitness payoff space is a mistake. In my view, Aharonov rescues both the common sense realism of the scientific revolution and the epistemological realism of Thomas Aquinas, which are the two colossal underpinnings of Western civilization that Hoffman has pitted himself against. All of this notwithstanding, Hoffman's conception of nature as a network of conscious agents is an interesting idea. If it's adopted, Hoffman and I seem to agree that it should have the very real goal of ridding the planet of nuclear weapons. An ontology that can deliver on this, other scientific things being equal, is preferable to an ontology that simply tries to prove mathematically that nuclear bombs aren't real. In any case, we'll continue our conversation and talk about Hoffman's most recent technical paper in our next conversation. As always, you'll find a timestamp in the video description, along with a list of relevant links. Thanks again for your time and interest. Here is my conversation with Donald Hoffman. Professor Hoffman, welcome to A Theory of Everything, and thanks so much for taking the time to talk.
My pleasure, Louis. Thank you for inviting me.
Well, I'd like to start by congratulating you for the incredible success you've had in spreading your ideas. I checked this morning, and your TED Talk has a total of more than 7 million views, and your appearance on Lex Fridman's podcast has more than 4 million views, plus the countless other appearances and lectures you give, and your books. All told, there are tens of millions of contact points with the world. So congratulations for that.
Well, thank you. I had no idea that TED Talk had that many views. So thanks for letting me know.
Well, we're here to talk about your recent book, The Case Against Reality, which is a great book. I read it and I was actually really surprised. It's really deep and really ambitious, much more than I thought. You're taking on not only the scientific establishment, but you're also taking on two big groups here. On the one hand, the scientific establishment who that insists on the reality being a physical, objective reality that's out there somewhere. But also you're taking on, philosophically, theologically, Thomas Aquinas and 2,000 years of Catholicism and the correspondence theory of truth. So you're taking on two arch enemies themselves, right? Because the physicalist approach is the enemy of the theological Catholic approach, but you've taken on both of them, so it's quite ambitious.
Right. It's my attitude is, of course, that I'm hoping for a good dialogue, and it's not about, in some sense, proving I'm right. It's about having a good dialogue and trying to move the ideas forward. Fortunately, the physicists themselves, as you know, are saying that space-time is doomed. So, in some sense, I'm just parroting what the physicists are telling us, that it's all over for space-time, and the work on evolution by natural selection, saying that we don't see reality as it is. Most of my brilliant colleagues who study evolution would agree. Steve Pinker, for example, would agree that the bulk of evolutionary logic clearly shows that we're going to be shaped to have false beliefs and so forth. He's very, very clear about that. The one place where they tend to hold back is to say, the one exception is, everyday physical objects at normal scale, middle-sized objects, tables and chairs. Maybe there we see some of reality as it is. And so in some sense, a deflationary way to think about what I'm doing is to say to them, well, yeah, the arguments that you guys give to say that most of our cognition need not be veridical also applies to everyday middle-sized objects. Here's why. So you can view it as just a minor correction to what they already know. So you can see but that minor correction has a lot of emotional baggage. So, the idea that the table doesn't exist when you don't perceive it, that gets us emotionally. So that's where the pushback comes from.
Okay, well, obviously, as you know, people disagree. Academics and everyday
Sure.
people disagree about just about everything, right? We seem to disagree much more than we agree on things. And one of the mission or the mission of this channel and our work at ASIM is to respond to this reality of people disagreeing. And one of the proposals, or not one, the proposal that we put forth to kind of put this situation into perspective is to talk about something that I think we can all agree on. And that's the fact that we should, if possible, we should avoid premature human extinction. So at the moment, as we speak, the world is full of nuclear weapons that could go off at any moment. So in your book and in your work, you argue against reality. So is this perception that we all share about nuclear weapons, is this an illusion? And should we stop trying to reduce the threat of an all-out nuclear war?
That's a great question. It really gets down to the issue of morality more generally. If we're not seeing reality as it is, what is the foundation for the good choices? What's the distinction between good and evil and so forth? And I think it's an extremely deep question. So, of course, my attitude right now is, of course, that I should be doing everything that I can to make life better for other people. And we should be avoiding actions like nuclear proliferation that could cause human extinction. I certainly agree, but there are deep philosophical and moral issues that come out of this whole approach to evolution by natural selection. If you want, we can go into this, but it's a very, very deep, the issue of morals and ethics goes very, very deep here. So I agree with you, absolutely.
Well, I didn't plan to, but I think that's an extremely relevant point, because the argument is that among all the disagreements that are out there about physics, about the nature of reality, about morality, etc., it seems to me, tell me if you disagree, but it seems to me that any argument that can lower the chances of human extinction is necessarily a preferable argument or a preferable framework or a disposition compared to a theory or a model that is absolutely irrelevant or has nothing to say about human extinction. Does that seem like a valid position, or would you disagree?
Well, First, I should say that personally, of course, I would argue against any position that leads to human extinction or even diminishes human flourishing in any way, right? I mean,
Absolutely.
I'm all for human flourishing.
Absolutely.
But so, I mean, that's my bottom line. The deep reasons behind that's a different story. I mean, to go into that in great detail is a long discussion. It's not a trivial discussion. So that's my bottom line. And if I don't know where you want to go with this conversation, but if we go into that will be the whole conversation.
Okay, well, we'll save it for another day if you're interested. I think that would be very interesting.
Sure.
But no, I didn't plan for that. I'd like to talk about the book and about the main ideas of the book.
Sure.
And about some possible objections and responses to those objections.
Sure.
So in what remains of our talk, and you've been nice enough to grant me an hour, so that's what I'll shoot for. So I'd like to talk about three major things. One is your idea that reality is in fact a network of conscious agents. I think that's a beautiful idea. I'd like you to expound on that. And then the idea that fitness beats the truth, that we don't really see the truth. That evolution selects for fitness and not for truth. And then the third idea, which I think is very interesting as well, is in the final chapter of your book, you talk about the growing convergence between science and religion, and you call for the possibility of a new modality of scientific theology. So I think those three ideas are very interesting. Can you talk about this idea that we are a network of conscious agents?
Right. So a little background on it is that in cognitive neuroscience today, one of the big open problems is consciousness, conscious experience. Something simple like, the taste of lemon, or the sound of a piano, middle C on a piano, or something like that. These elementary experiences, which we just take for granted, they're just part of our everyday life. We don't even think about it. They turn out to be extremely difficult to explain if you start with neural activity. And this is called the hard problem of consciousness. Most of my colleagues think that brain activity somehow creates our conscious experiences, like the taste of a lemon. And we do have lots of data that show that there are these correlations between neural activity on the one hand and specific conscious experiences. These are called the neural correlates of conscious experiences. And there are scores, maybe hundreds of these. So there's a lot of good empirical data that there are these correlations. And most of my colleagues assume that somehow the neural activity is causing the conscious experiences. But remarkably, and again, these are my friends, my colleagues, they're brilliant. These are really, really smart people. But there's not a single experience that they can explain, not one. They have all these theories, but there's not one experience on the table, like the taste of vanilla. Not one experience that they can say, this is the pattern of neural activity that must be the taste of vanilla. It could not be, a headache or whatever it might be. And these are the principal mathematical reasons. There's literally nothing on the table. So there's lots of empirical data, no theories. There are no theories on the table that can explain even one specific conscious experience. Now that's stunning. Usually in a science, we have some successes. We have certain cases that we can explain. Here we have zero. And so that's a problem. I mean, that's a deep problem for our field. And so one approach is to say there are no conscious experiences. Dan Dennett and Keith Frankish and other brilliant philosophers, and they're wonderful, brilliant people. They say this problem is so hard. We're just not gonna have any conscious experiences. We have the illusion of conscious experiences, but there are none. But most of my colleagues, I would say 99% of my colleagues say, no, there really are conscious experiences, and we do need to explain them. So the approach I'm taking is to say, look, we have good reasons, and we'll talk about the reasons from physics and from evolution by natural selection. We'll talk about that later, but we have good reasons not to take the brains and neural activity as fundamental. And so they're not the source, they're not the cause of conscious experiences. If we're going to have conscious experiences, why don't we try taking them as fundamental? And the argument might go like this. my colleagues who are trying to explain conscious experiences, they assume that there are physical objects like brains and neurons in space and time. They then assume certain properties of those brains and neurons, like integrated information or orchestrated collapse of microtubule quantum states in certain neurons and brains. Or there are various kinds of organizations of physical systems that they assume. So they stipulate space and time in brains. They stipulate certain patterns of activation, but then they're forced to stipulate the conscious experiences. They have to stipulate, and this corresponds to the taste of a lemon. This corresponds to the sound of a trumpet. So they're stipulating everything. There's nothing that's actually explained. So my attitude is, it's good science to have as few assumptions as possible. So instead of stipulating space and time and stipulating neurons and stipulating these patterns of activity, let's just stipulate the conscious experiences, because my friends have to stipulate them anyway. So I'm only going to stipulate that there are conscious experiences, and then my job is to explain everything else. I'm going to then explain where space and time come from. I'm going to explain how neural activity arises from a deeper network, a deeper theory in which there's only conscious agents. So to make that, so it's one thing to talk about that at top level. It's another thing to make it a scientific theory. So what we've done is to say, here's a precise mathematical definition of what we mean by a conscious agent and its experiences. And here's a precise mathematics about how these agents interact. And we published it in 2014 in a paper called Objects of Consciousness. So that paper is free online. So if you just Google Objects of Consciousness and my name, you can get the paper for free. And so we're then using that mathematics to then take on the problem of how do we boot up space and time, and then once we do that, then how do we boot up objects in space and time, like like protons and the bosons, leptons, and quarks, the elementary particles, and then protons and neutrons, and then bigger things like brains ultimately. But we're going after the easiest stuff first, which would be the bosons, leptons, and quarks. That's going to be the easiest thing to try to boot up. So yeah, we have this whole notion of conscious agents outside of space and time. And space and time is just one kind of data structure that certain conscious agents use to interact with other conscious agents. That's at top level. But intuitively think about it like a big social network, like the Twitterverse, right? There are a lot of people tweeting. There's millions of Twitter users, billions of tweets. It's too much to try to interact with all the Twitter users and all the tweets. So we use interfaces. We use like look for trends. What's trending right now on Twitter. And that's what space and time and physical objects are. It's a little user interface that we use to interact with this whole social network of conscious agents. So that's just a high level kind of accounting. And for those who aren't happy with a high level accounting and want the math, then you can go to the Objects of Consciousness paper.
Excellent. So what you're positing then is a reality or an ontology that begins below space and time.
Right.
And then your goal is to demonstrate how, from this fundamental reality, we get to quarks and leptons and gluons, et cetera, to physics, and then to chemistry and biology, trying to connect this to our initial idea that it's better for humanity to not go extinct. Would it be logical to then take the step further and connect, if it's possible, connect the same physics and the same math, the same model, to some of the biggest open questions in political theory and social choice theory, et cetera? Do you think that's a logical next step?
Absolutely. The ethical implications of this are transformative. A lot of the traditional ethical and moral questions get placed in a completely new light when you start to think about consciousness outside of space and time, and space and time and physical objects as merely a headset, not the reality. And then you even come to questions about the very nature of, for example, our entire universe, the Big Bang, through everything that's happening right now, through the perhaps entropy death of the universe. All of that takes on a completely different meaning and a different explanation from this other point of view. So some of our deepest held assumptions on which these moral issues are discussed get deeply challenged by this new framework.
Excellent. Well, I think this is very interesting and promising, because just last week we talked to the Fields medalist, Michael Friedman, on a recent paper where him and a couple of colleagues posit a connection between quantum theory, quantum field theory, especially concretely the Born rule, and some new political theories and political ideas. So it would be very interesting. And I think there is some possibilities to merge a lot of the mathematics that you're working on with some of the work that they're doing, and to transform the way we think about how we make collective decisions and how we manage the planet. So it's quite exciting. And one of the reasons that I insisted on opening the conversation on anchoring this, we're in a bad situation on the planet as humans. We need to address that. If we can address this at the level of, fundamental ontology, it sounds to me that we are on a much more solid ground. So it's quite interesting. As a matter of fact, Michael Friedman's work in collaboration with Glenn Weil, they're both, Glenn Weil's an economist at Microsoft, and Michael Friedman is one of the most instrumental persons behind Microsoft's quantum computing strategy. In fact, he was the managing director of their quantum program for many years, the founder and the managing director. Where was I going with this? Their work is also connected with a group of people that I think you're very well connected to, which is Karl Friston and Chris Fields. Can you talk very quickly about your work with Chris Fields?
Yeah. Chris is a good friend. He's a brilliant thinker, and we've worked together on the conscious agent network stuff. And he's also very, very well aware and expert in a lot of aspects of quantum theory. And he's been looking at, he's collaborated also with Karl Friston and the Markov boundaries, Markov blankets kind of idea. And so this is it's all deeply related. And in terms of the conscious agent network stuff is this network then, and when you have what I call user interface on these networks, that's like a Markov blanket. So there's deep connections between the notion of Markov blanket and the notion of a user interface, and also the notion that space and time is just a headset. These are all deeply connected ideas.
Yeah, very fascinating. And it's also interesting that Karl Friston recently accepted a position in the private sector, working on artificial intelligence and trying to bring these ideas, just like Glenn Weil and Michael Friedman are trying to connect these ideas to the everyday world. It seems like we're at a very promising historical juncture, and I think it's quite exciting to witness all of this.
Yeah, I think that the technological advances that can come out of these ideas, like of consciousness beyond space-time, are truly stunning. Once we recognize that space and time are not fundamental, which is huge. I mean, physics and science has taken space and time as fundamental for centuries, or space-time more recently. But once we realize that space and time are not fundamental, and we start to take the first steps beyond space-time, as physicists are doing, they found the amplituhedron and decorated permutations. That's the deepest thing right now, is these decorated permutations that they found. And then we're working on these conscious agent networks beyond space-time. And in a paper that we just got accepted last week and just submitted the final paper this morning, we actually show how in this paper, the decorated permutations that the physicists have found beyond space-time are a projection of our conscious agent network. So we actually show how their decorated permutations arise from our conscious agent network. So in some sense, we're discovering the first layer of software beyond our space-time headset. Once you know the software and how it works beyond space-time, you can play with space-time. So right now, And so I'm looking forward to the technological implications of it. Right now, if we wanted to go to our nearest galaxy, the Andromeda galaxy, it would take us 2.4 million years. It's 2.4 million light years away. So that's 2.4 million years going at the speed of light. If we go slower, it's going to take longer. But the fastest we could go there is 2.4 million years, which means even your great-great-grandkids on the spaceship won't get there. But what if we don't have to go through space-time? Because space-time is just a data structure. It's just our headset. What if we know the software that programs up the headset? Then we could just go outside of space-time. So instead of going through space-time, we could go around space-time. So the technological implications and the possibility for human flourishing of these technological implications are truly mind-bending. I can't wait.
I agree.
I'm eager to get them.
I agree. It's very interesting. There's also the religious implications, but we'll get to those at the end, because I'm reminded of some of the things that in Christianity, for example, that Christ says, and some of the things that he supposedly did, like rising from the dead, asking his followers to feel his flesh, et cetera, et cetera. But we'll wait for that. We'll wait on that till the end. Okay. So you have been working closely with the work of Nima Arkhani Hamed, and his work on permutations and the amplituhedron.
Right.
But as your interview with Curt Jaimungal on theories of everything, as he pointed out, there's other possibilities. There's other frameworks that respond to the idea that space-time is not fundamental. And in that case, you responded to his objection or his question of why this framework as opposed to others. Do you still stand by the Arkani Hamed's framework being the best framework to proceed?
I think that his team has just in the last 2 years used their framework to be able to get all scattering amplitudes for all spin and all masses. So their framework is, a few years ago you could have, and people did, they would argue that he only was able to compute so-called scattering amplitudes, like 2 gluons hitting each other, 4 gluons spraying out, getting the probabilities for these kinds of interactions of particles. People could, until a couple of years ago, say it's only for supersymmetric massless particles that this thing works, and so it's only a toy model. So he's got this stuff beyond space-time, but it's just a toy, and it doesn't really get you all the particle interactions we're interested in. That's no longer true. What he's been able to do is to show that it's not just supersymmetry, it's not just massless particles, they're getting all spins and masses and so forth. So the other thing that's really interesting about his approach is he's saying that it's not just that space-time is doomed, it's quantum theory that's doomed. So that because space-time and quantum theory are deeply connected, and what he's showing in his work is that when you give rise to space-time, you also give rise to quantum theory. So his structures, for example, do not require any Hilbert spaces, right? You need Hilbert spaces for quantum theory. So his structures, the amplituhedron, don't require unitarity. They don't require locality. They're just entirely beyond space-time and beyond quantum theory. But they show how space-time and quantum theory sort of arise together, join together. So my take right now is his is the most promising work about what is going on beyond space-time. Other physicists that I've looked at they'll go part of the way. They might get rid of space, but they don't get rid of time. For example, they still want to hold on to time being fundamental. And I think that Nima and the other guys at the Institute for Advanced Study and their collaborators. So this is the Institute of Advanced Study at Princeton. These are this is not just some small group. These are pretty bright people. And their collaborators, they have really jumped outside of space-time with both feet. They're really committed outside of space-time. And my take is you can't go part way. You have to recognize that space-time is just a data structure, and frankly, a fairly shallow one, 10 to the minus 33 centimeters it gives up. So it's a fairly trivial data structure, a very shallow data structure. And we just have to, it has a grip on our imagination. It has for centuries. It's time for us to let go of it, resist that grip, and free our minds to look beyond space-time, entirely beyond space-time, and entirely beyond quantum theory, and then show precisely how space-time and quantum theory arise as projections of this deeper. And so his work seems very, very promising in that regard. And our work on conscious agents, what we're doing is showing how it projects down to the decorated permutations, which he's found beyond space-time. So we're connecting, he's gone beyond space-time and found decorated permutations. And so we're connecting our theory of conscious agents to those decorated permutations.
Very nice. And then your model of conscious agents then maps onto Karl Friston's conception of graph and graph theory. Is that correct?
Yes. So these networks of conscious agents can be described with graphs. They're very dynamic, but they are graphs. And the notion of Markov blanket that he talks about quite a bit, which is of course from Judea Pearl and the work on Bayes nets that Judea Pearl originated. But the idea that you have this big graph, this big network, and you have nodes of the network inside the Markov blanket. Then you have the Markov blanket, and then you have the nodes outside the Markov blanket. And the idea then is that the nodes inside the blanket and the nodes outside the Markov blanket are conditionally independent of each other, given the state of the blanket. So that in some sense, what this all boils down to is the Markov blanket is like a user interface. So you have the set of the graph inside the blanket can only see the outside world via the blanket, and that's just like its headset. It's its user interface, and it can't really know the true state of the world. All it can know is the state of its blanket. What's on my headset is all I can see. What's on my VR headset is all I can see. And so Friston's ideas are very, very close to ours in that regard, and also our work on evolution, which indicates that space and time and objects are just, again, a headset, not the reality.
Okay, very interesting. If it's okay, I'd like to transition now to your idea of fitness beats truth. Can you give us a quick summary of this idea and the research behind it?
Right. So Darwin's theory of evolution with natural selection, of course, assumes organisms in space and time. Right. There are creatures red in tooth and claw fighting for each other, and they, in our modern synthesis, they have DNA and so forth. So it's all about physical objects in space and time. But John Maynard Smith and others have turned Darwin's theory into a mathematically precise theory. And they use what we call evolutionary game theory to study evolution. And so with the mathematics of evolutionary game theory, we can ask precise questions like, what is the probability that evolution would shape our sensory systems to show us true structures of objective reality? In other words, to put it, what's the probability that we would see the truth, in whole or in part, if evolution were shaping our sensory systems? And so you might say, well, look, the evolutionary theory already assumes that it's true that there are organisms and DNA. It's assuming, but the mathematics allows us to abstract from that. So the mathematics of evolutionary game theory allows us to ask the technical question, would evolution shape sensory systems to show true structures of objective reality? And when you look at the math, the answer is the probability is precisely zero. And again, for those who don't want to take my word for it, I've got a paper with Chetan Prakash and other co-authors called Fact, Fiction, and Fitness. So if you just Google Fact, Fiction, and Fitness and my name, you can read the paper for yourself. I believe it's online for free. So you can just read the math yourself. But we have some other papers too. There's a paper called Fitness Beats Truth.
By the way, I will provide listeners with all of the relevant links in the video description.
Okay, well, thank you. So these papers are out there for people who want to see the math. It's out there. The bottom line is, evolution is a mathematically precise theory, and it says the answer is precisely the chance is zero that we've been shaped to see any aspect of objective reality. So that means that space and time and physical objects, even the three-dimensional structure of space, 4 dimensions when you think about space and time, is not the objective reality. That's just a user interface. It's just a headset. And so that's what we call the fitness beats truth theorem. And if we want, we can go into the technical details of it, but right now I'll just stop and say it's a theorem of evolution from the math that the probability is zero that any organism sees any aspect or perceives any aspect of objective reality as it is. That's what the theory of evolution says. Now, I don't know if that's true or not. I'm just saying that that's what evolution entails. If you buy evolution, then you're forced to that conclusion. The question about do our perceptions match reality in another framework is an open question, right? But within the evolutionary framework, it's not a question. It's not an open question. It's a theorem.
Okay. Although Curt Jaimungal raises an interesting objection, he says that the argument that it goes to zero depends on an assumption, and the assumption is that there's an even probability, right, of all of the possibilities. And you've responded to that objection. Now I don't recall what your response was. In essence, you said that this is the challenge. If anybody believes that this is not the case, then the burden of proof is on them to provide an argument to explain the conspiracy in nature that favors one set of functions over others, or a fitness payoff. Is that the case?
Right. That's right. Exactly. So this is a little technical thing, but I'll go into it. So in evolution, the evolution is governed by these functions called fitness payoff functions. They determine for every, organism, state, and action that it might take, is that going to be helpful to the organism to survive and reproduce, or is it going to be detrimental to the organism in terms of survival and reproduction? And so these are called fitness payoff functions. And our mathematics looks at the set of possible fitness payoff functions. Now, we right now assume that all mathematically all mathematically possible fitness payoff functions are relevant and equally relevant. And on that assumption, then the probability that you run into a fitness payoff function that would give you the truth, that would shape you to see the truth, is probability zero. And that's the current state of evolutionary theory, that all fitness payoff functions are equally likely. Now, if someone wants to change evolutionary theory and say, no, there are a certain class of fitness payoff functions that should have higher weight, perfectly fine. But you would then change evolutionary theory. You would need to then, have your revision of evolutionary theory in which certain payoff functions are in fact metaphysically more likely than other fitness, and argue for it. So that would be a new theory, and I would welcome someone to try to do that. But given the current theory of evolution, there's nothing in the current theory of evolution that says we should give more weight to one fitness payoff function over another. And when you go with current evolutionary theory, then probability is zero that you'd run across a fitness payoff function that would shape you to see the truth. So, but absolutely, game on for anybody who wants to show that there's a different weighting on the fitness payoff functions that's perfectly acceptable to evolutionary theory. I would love to see that.
Well, very interestingly, we had another guest, Eliahu Cohen, who has worked with Yakir Aharanov and his team on the two-state vector formalism, which posits two boundary conditions, one that evolves from the past to the present, and another that evolves from the future back to the present. And so what we experience as reality in the present is the conjunction or the meeting of those two wave functions in the present. And this, they claim, solves the measurement problem. And I see it as a very interesting model that is not only intuitive, but it maintains the idea that no, what we are seeing really is real, and it's really out there. So it's a very different approach, comes to a different conclusion, but it shares a lot of overlap with what you're trying to do. So my first question is, I didn't read it anywhere in your book or in your papers, what your model of conscious agents says about the measurement problem. Can you say something about this?
Right. So the measurement problem in physics arises from quantum theory, right? And in quantum theory, the way you describe a physical system is very different than in Newtonian physics. In Newtonian physics, you say there's a particle at this position with this velocity, and you know it's all spelled out. And you might have some statistics about it, but in quantum theory, you put down these complex valued wave functions. So it's not real numbers, it's imaginary numbers, and you have a field of imaginary numbers that's evolving over space-time. So in quantum field theory, you have these fields of imaginary numbers, and they're evolving over space and time. And if you want to ask, okay, well, what is the position of the electron, right? Well, when you start you're dealing with imaginary numbers, there's not any real position. So when you actually go to ask what is the position of the electron, you have to perform some intervention. And the way that you mathematically model that intervention in standard quantum theory is that you have this wave function, and it collapses down to some specific value that you get. So there might be a whole distribution of complex values that would allow a wide range of, say, positions or momentum for the electron. But when you actually look and do a measurement, then you get a specific value, like there's that position X. And if you prepare the same electron an electron in exactly the same state, as best we know, exactly the same state, and you measure its position many, many times, you won't get the same answer every time. Every time you measure it, typically you'll get a different answer, but you can predict the distribution of those answers. And so the measurement problem is, what in the world's going on here? Why do we have to use these complex numbers when we don't look? And what does it mean to measure? And why is it that we get different answers, even though the state of the electron is the same? We get different answers every single time. And so that's called the measurement problem. And it's been there's been lots and lots of ways of trying to deal with it. One, some people say that the wave function really collapses, is sort of the von Neumann kind of approach, where you say that there's a collapse that the measurement does. Others, like Chris Fuchs, say, yeah, I'm sorry.
How does the conscious agent network respond to this?
So the conscious agent network will say that the reason why we have to use, like in quantum theory, these wave functions is because space and time are not fundamental. What's really fundamental is a dynamics of this Markovian dynamics of conscious agents outside of space-time. When you project that complex dynamics and look at it through a space-time headset, it's going to look like a complex set of waves. and any projection that you get into your headset will only be not the truth. It's so, because all you're going to get is a value like in a pixel on your headset, but the pixel is only a property of your headset, is not a property of the conscious agents outside. So it's very, very clear where where the wave functions come from, and why you're not going to have a value of the physical property until you observe, because the physical properties don't even exist when they're not observed. So our solution to the measurement problem is to say, the reason why you have the measurement problem is that physical objects and space and time themselves do not exist when they're not perceived. They are headset descriptions that we create when we need them, and we delete them when we don't need them. So that's our approach. That's the top level. The mathematics is deeper, but top level, we say the reason why we have the measurement problem in quantum theory is because the electron doesn't even exist when it's not perceived. It's merely a data structure that we create on the fly and delete. So like if you have a virtual reality headset on and you're playing Grand Theft Auto, and I look over and I see a red Camaro in the Grand Theft Auto, I create that red Camaro on the fly when I look, and when I turn my headset, I delete that red Camaro. It no longer exists. The supercomputer that's running the game has no red Camaros in it. So the red Camaro is entirely my creation. So that's where the measurement issue and measurement problem comes up, and that's how we resolve it. I create the Camaro when I look, then I look over here and I see a green Porsche. I create the green Porsche, and none of them exist when I don't look, because they're entirely interface headset icons. So I create the icon when I look and I destroy it when I don't. So the reason why the measurement problem seems so counterintuitive to everybody is we assume that space, time, and physical objects are real. We assume that they're there when we don't look. And so we get all confused. Why does the electron position keep jumping around? I mean, the electron's really there. It has a real position. No, it doesn't. And the electron isn't real. It's just an icon that you create on the fly. So that's our take on the measurement problem.
Okay, yeah, obviously that's the central part of your argument, or one of the central part of your argument, and it's obviously radical for some people. It's it's difficult to accept. So I'm going to, if it's okay, share my screen very quickly.
Sure.
And for the sake of listeners, and also just for the sake of discussion, I'm going to share some of the work of Eli Cohen, who visited the channel in the past, and the benefits of using the backwards evolving state. So in terms of in the context of our conversation, the backwards evolving wave function would respond to your question or your challenge to identify what it is in nature that's giving preferential weights to different fitness payoff functions. And the idea is that this backward evolving wave function determines how we experience reality, including evolutionary theory, including everything that we experience in reality. So there's some kind of goal state in the future that determines how nature itself evolves. So very quickly on the screen here, we see a number of the benefits of using this backward evolving state. It sounds very new, very counterintuitive, very radical. But you'll see in the list of references a who's who of physicists and other scientists, including Lev Weidman, Scott Aronson, Yakir Aharanov, Juan Maldacena, Paul Davies, that all use this model to actually produce physical results in reality. So it's not theoretical, it's actual science that's taking place at some of the leading teams and laboratories throughout the world. And not just theoretically, it actually leads to, for example, advantages in quantum computation. It leads to advantages in metrology and a host of other advantages in several other areas of physics and math. So I'd like to listen very quickly to Eli Cohen. So listen just for a minute or two to what he says about the benefits of using this this two-state vector formalism.
Okay.
But this again is our scenario. So we have initial condition going backwards in time. We have final condition. I'm not sure who put it. I'm not sure how it arises. I'd like to, but I don't know. What I do know is what to do with it. And I'll show you what we can do with a final boundary condition put now on the universe. And the meaningful object, the important thing to discuss now is not the state vector, it's the two-state. So the two-state now gives rise to something else, to a two-time density matrix. We don't discuss anymore density matrices. We are not concerned now with many problems of entropy of density matrices, because we now have something completely different. It's a two-time density matrix. And Yakir asked, how can we feel these future effects? And we now know the beautiful answer. We can sense final boundary conditions using weak measurements. So we just replace the von Neumann coupling with a very weak one. We can talk now about several things. The first thing I'd like to mention is that, as Alonso said.
Okay, I'll pause there just very quickly to mention this research program of weak measurements is actually very, very well established. And has led to significant fruits in many different areas.
Sure.
And so the idea here being that a lot of what we see, so you're a vision scientist, I think it would be interesting to compare and contrast. We don't have time today because we've just run out of time. But at some point in the future, keep thinking about this possibility of how a future boundary condition, in the case of our conversation, for example, one future boundary condition, we can imagine, cartoon it like a planet with no nuclear weapons, where they've been eliminated. Okay, how does that future boundary condition impact the present? And this model would then determine all of the decisions that the various players make along the way, and also the quantum systems on which they're founded. So that's the idea. And here it's a quite different approach than your approach, but in some sense it salvages the idea that it's much more intuitive that no, we really live in a world that's on the brink of nuclear destruction. In any case, either way, whether it's an illusion or whether it's real, we've agreed that what we want to do is stop that possibility. And I think this gives us a series of interesting tools, in addition to the tools that we're already working on, to get us to that final goal. And I'm really sorry we're out of time for today. You've been very generous with your time, Professor Hoffman. And we didn't get a chance to talk.
Respond a little bit to the.
Sure. Yes, please do. Please do. Yes.
Yeah. Right. So I think that that's wonderful work, and I think that the technological and intellectual advances there are genuine and wonderful. But I think that even though I think it's extremely powerful, the very notion of time itself, whether forwards or backwards, ceases to make sense at 10 to the minus 43 seconds. So ultimately, whether we are thinking about forward and backward time, at the Planck scale, time ceases. And so Juan Maldacena, who was mentioned there in a 2004 paper, now has some work with Nima Arkhani Hamed, much more recently in 2018 or something like where they're looking at something called the cosmological polytope. So Juan Maldacena is now looking for the structure entirely beyond space-time that is timeless. It's a geometric object called the cosmological polytope, but on one of the facets of it, you get what I think is some kind of energy facet, zero energy facet or something. Anyway, you get space and time, whether you're thinking about time going forward or backward, you get it as just a projection of a particular facet of the structure beyond space-time. I think the Aharonov ideas are fabulous and so forth as far as they go, but they're still stuck in the space-time headset, and that whole headset has to go, including quantum theory. That's quantum theory going forwards and backwards. All of that's going to have to come from a much deeper framework. Now, the burden, of course, on this deeper framework is to show how the Aharonov stuff comes as a projection of a much deeper and framework beyond space and time themselves. I'm working myself on exactly that. I'm trying to show, and I'll just briefly say, this conscious agent network. When I take a big Markovian dynamics and I look at its projection on a subset of states, this is called a trace chain in Markov dynamics. I want to show that I get the Big Bang, the evolution of the universe, the appearance of matter, and then eventually entropic death, all as an art. So at the whole time, whether we think about time going forward or backward, all of that turns out to be an artifact of a trace chain operation. And so that's the direction where I want to go to, beyond space and time, where we would show how these kinds of forward and backward quantum ideas arise as artifacts of a projection of a much deeper thing. So that's where, again, I think the powerful work ahead is going to lie. The Aharonov stuff is extremely useful and extremely powerful, but I want to show that it's a projection of this deeper framework entirely outside of space and time.
I think Aharonov would agree with you, and his team would agree with you. It's
obviously
there's obviously a more fundamental ontology, but I think we also agree that from that fundamental ontology, we want to come back to this level of reality, and so that's that's the interesting part. Yeah, that's the interesting part.
I couldn't agree with you more. Anything that we propose beyond space and time must project to the theories that we know and love inside space and time, or the deeper theory is wrong. So that's the constraint on any deeper theory we propose. It better give us back quantum field theory and Aharonov's work. If it can't do that as a special case, then our deeper theory is wrong. So I absolutely agree.
Excellent. And we've also agreed that when we come back to the everyday physics that we know, it's also preferable for a model to save us from destroying ourselves than for a model that is absolutely that says nothing about that. No?
Well, I would say, at first blush, absolutely yes, but the issues there are very, very deep and deserve a lot of discussion. But the answer for one word, yes.
Professor, well, thank you so much for your time today. I appreciate it. Tell us what you're up to now and what people can do to follow your work and your activity. What's next for you?
Well, so we have a paper that's going to come out probably this month. We just turned in the revised paper. It's been, gone through the reviewers this morning. So it's been turned in. It's going to be called Fusions of Consciousness. So if people want to see our current work, it's going to be in the journal Entropy, ENTROPY, Entropy. The journal Entropy, it's called Fusions of Consciousness. It's where we show precisely how to take the conscious agent dynamics, project it into decorated permutations, and then use that to connect with the physics work that Nima is doing. So our next paper, I'm tentatively calling Traces of Consciousness, where we're using trace chains on conscious agents to show that we get all of physics. I want to show how the quark and gluon C inside of protons arises from this trace chain idea. So I'll be working on that. I mean, for people who are interested, I have and want to see what I'm up to. I have a Twitter feed where I always tweet my latest talks and podcasts and so forth. And I'll be tweeting this paper as well when it gets published. It'll be free, by the way. It's going to be free to the public. So Fusions of Consciousness and Entropy will be free. So I'm pretty excited about where we're headed. We're to the point now where I'm looking at cosmological things, trying to show the Big Bang to the entropic death arises from trace chains, trying to show how quark and gluon Cs and the whole quark structure of protons could arise from this theory of conscious agents. So a lot of fun ahead. But my Twitter, for those who want to follow, is Donald D. Hoffman. So Donald, then D, and then Hoffman, all one word. Is my Twitter handle. So
fantastic. You've been so generous. We didn't get a chance to talk about this. I'd love to have you back to talk about your recent paper and its implications for religion. Would you be interested at some point?
That would be perfectly fine, because there are a lot of interesting religious implications, or spiritual traditions, more implications more generally. So I'd love to. We'll set up a time to do that.
Well, one final thought. I think where religion and science converge is on the concept of salvation. What I've been talking about today is we want to avoid human extinction. In a religious context, we might interpret that as salvation.
Sure.
And religion in a non-religious, from a non-religious perspective, we might refer to that as avoiding death, in this world. So exciting.
Right. No, I'd be very, very happy to talk about the Christian ideas or Eastern mystical ideas and the Christian idea about the kingdom of heaven and so forth. These would be fun things to discuss from this broader framework. So yeah, let's do it.
Okay, fantastic. Thank you so much. Talk to you soon. Look forward to talking again.
Thank you, Louis.
To support our discussions with the world's leading thinkers, Please see the video description or visit eism.eu/support. Thank you.